sixth interactive session. Let us first look at the contents of our sixth lecture. I believe that we covered everything from fifth week lecture, but let me, yeah, we did some questions on this. Uh, See, for this, there is not much to be mm, discussed. These are just how, these are just like I explained to you how they talk about a point, and when we are talking about a point, we are no longer we are no longer talking about plane strain condition. In 3D condition, we will have to go with cylindrical coordinates or maybe uh, Cartesian 3D coordinates. So that is why you see this R and Z, and that is why you don't see this in other topics that you study, except for you will see this in aquifers, except but that is not because it's not plane strain, it's because the radius of the well is not taken as the semi-infinite dimension. So, okay, excuse me. So the most accurate value can be obtained using the same Buzenisk formula, but suitable modification. Entire foundation area can be divided into number of small units. So we divide this into number of units and then apply the same formula to this again and again. This okay. Then this see this is what is see obviously everything is important because all the theory of somebody raised their hand. Yes, yes, Arav.
Good evening, madam.
Good evening.
I have a small doubt, madam.
Yes, please.
Uh, is the Bosniak's theory applicable even for rock also? Because I saw this question somewhere in the exam.
I'm not very well versed with rock mechanics, but I can't see why not.
Mhm. You can clarify in the next class, madam.
Yeah, I
It
can.
maybe I saw it in NPTEL exam or somewhere. This one
Okay, but
they have given
yeah,
option ABC.
I can't see why not. It why should it
Okay,
not be? It can be, I think.
okay, madam. Okay, madam.
Okay, so as I was saying, this is what uh, obviously the whole part is important because this is actually where you derive your um, all the equations for your bearing capacity in shear strength problems. That is the main, like right now we are studying, this is the basic. Then in the advanced course, the most important thing that as a geotechnical engineers you have to do is calculate the bearing capacity of structures and the strength of the soil, and all of that it depends on this concept only, this concept of stresses under soil. But this is specifically important for us because usually we are not faced with point loads, we are faced with like foundation you will have, it will have some stress, it will have some area. It cannot be a point load you can take as a pile or something, but shallow foundations you will have load like this. So it talks about how we calculate, as we mentioned earlier also, that the stress will travel like a bulb. So this is approximated as this 2:1 distribution on either side. Okay, so because we take plane strain, we are not concerned with this direction. What we are concerned with is this distribution. So why this is important? Because let us say that I have a soil strata and it has a soft clay layer here, and I want to construct something over it. I want to know that how much load I can put on this so that the bulb of pressure does not cross this, because I know that the soil is soft and my structure will fail. So I approximate, if this is the depth of your weak layer, then this will be n times z, n times z. This will be the uh, effective area. So the force, the load you put over here will be distributed over a greater area here. It's not, if this was L, at the surface we will have a pressure of Q by L, but at this level of soft soil we will have a pressure of Q by L plus Nz, 2 Nz, and B plus 2 Nz, isn't it? So that is how we basically calculate how the stress will propagate in the soil and what stress will there be at a particular depth. Okay, so like this, uh, we talked about this. We have a length and a breadth, and then the effective area is larger than the actual area based on the depth. That is why with depth you can see that the pressure uh, applied to the layer decreases as the depth increases. Okay, so 2 BF, 2 LRF, basically 2 BF plus Z, 2 LRF plus Z. It's the same thing that we discussed just now. Okay, yes, we discussed week 5, then we are week 6. Yes, Arav.
Madam, in the same topic, I have extension of one small doubt, madam.
Yes, please.
It was exactly final exam last semester, madam, soil mechanics.
Okay.
IIT Bombay, they have asked this question. In the ground, normally we have either rectangular, square, or a strip footing, or any of the circular footing. These are the formulas I know about how to calculate
Hmm.
stresses by 2:1 distribution method.
Hmm.
But last time the examination question is it's a triangularly varying load is given.
Okay.
Uniform, yeah, triangularly varying load, like embankment, both the edges will be there, na triangularly varying load.
Yeah.
Like that, they have given the load itself is a triangularly varying from 0 to some x value.
Mm-hmm.
And further, they ask you to calculate what is the stress at particular depth.
Mm-hmm.
I don't know what is the source where I can find the solution. That's why I'm asking you.
So you're
Maybe,
saying, okay, okay.
yeah, you can draw the diagram, madam. I will show you.
Yeah. So you're saying that there is a triangularly varying load on the
That's all.
footing,
Uh,
and we have been. So the easiest way would have been, the easiest way is you calculate an equivalent UDL,
Rectangle. Uh-huh.
an equivalent UDL,
Okay.
isn't it?
And then remaining procedure is same. Huh?
And then the remaining procedure is same. Or uh,
Hmm.
I think
Yeah, I
this
will try, madam. This method I will try as you told, converting into the
also
rectangle or
also this can be, see, if you can see, there is kind of a moment on it, isn't it? So you
mhm.
calculate the P effective, the triangle will have the centroid here. So the whole P you concentrate here, and then there is this moment, isn't it?
Eccentricity. Hmm.
It will be P and E.
Hmm.
Then you solve this. There are certain ways like Meyerhoff's method that for foundation that use these things for the moment also.
Okay, madam. Okay.
Okay,
Right, madam.
there these are two ways that I can think of off the top
Hmm.
of my head. Rest, if you find some more elegant solution, please, I would like to hear about it.
Okay, madam. Thank you.
Okay. So, uniform contact pressure under rectangular footing. This is a question. Okay. Question week 6 is mainly about shear strength. So, we will discuss the shear strength first, then we will do some questions. Okay. In many soil mechanic problems, the shear strength of the soil emerges as one of the most important characteristics. S- Shear strength of the soil is the most important characteristic of soil actually, because as I mentioned earlier also, soil is soil does not fail in compression. Soil does not have tensile strength, and the only kind of resistance it is providing to any load on it is shear resistance. Basically, what is happening is, let us say that I am walking. The load that I am putting on the soil, it is creating a failure surface type of thing. Let me say, let this be a block of soil that is has a cohesive property. As I push the ground, this block will try to move in the inward direction. Okay, and this rest of the block will be stationary. So we will have a shear stress developed on this surface. Okay, so that is basically how the soil, uh, in any direction, what it does is that the surrounding soil will be stationary, and there will be a failure surface along which the soil will try to move, and the rest of the soil will try to stop this motion. Anything that you have, let us say that you have a foundation. If it is sinking vertically, then you will see shear strength, shear resistance here. If it is tilting, let us say like this, so it will form a, this kind of wedge, and you will see shear resistance on this. If you have slopes, okay, let us say that the slope is too steep, you will have this kind of failure, and the resistance to this failure will be along this surface, which is your shear resistance. So it is the single most important property of soil, and that is why it is very extensively studied, understood, and comprehended. So we will now let us try to imagine how material like soil will provide resistance to a load. We have already talked about effective stresses and total stresses. We have talked about water pressure. Now we'll talk about shear strength. So any section of soil, let me say I have put a load in here, and then any kind of distribution of loading there is. Let me say that this is a block of soil that is experiencing a compressive behavior here. Okay, and can be compression or tension here. Let us say this. Compression is, let us say, 100 kPa, while you're in the opposite, in the orthogonal direction, your compression is 50 kPa. You see, you are you are putting only normal stresses on the soil, but this will result in a shear stress. Why? Because these are not equal. If they were equal, you would not have had experienced a shear stress, because it's like a fabric. You take a fabric, and four people are, let's take a square fabric for example, because there are two orthogonal directions, and four people are standing here, and these two are pulling like this, these two are pulling like this. If all of them are pulling in the same with the same intensity, what will happen is that fiber will be taut. It will still be a square, and it will be stretched. But let us say that these two are not pulling their weight, and they are not pulling it as they should. So what will happen is that you will see that there will be a distortion in the fabric. Okay, so um, the distortion will be in the in this direction. A resultant force will be there, and you will see that the fabric will become something like this. That is what happens in soil. It's not like uh, when we say that the soil has experienced some shear stress. It does not mean that I'm exactly putting in a shear stress, as in the shear stress will be something that you um, uh, pure shear is something when you have a body and you are loading it like this. But right now I have put a weight here which is just perpendicular here. I have not put any shear stress here. This is not shearing. But what will happen, that surfaces will be formed along which there will be shear stress. And that is why we need to talk about it. And also, so the first case is you are providing a compressive stress, but there will be other surfaces on which there will be a shear stress. And the second point is that in a particular, let us say, body, if there are unbalanced stresses, they will result in a shear stress, irrespective that you are providing pure shear or not. So shear strength is important for stability of slopes, ultimate bearing capacity of soil, lateral pressure against retaining walls, sheets or bracing, friction developed by piles. Um, okay, so what uh, the researchers believe, what are the properties or what are the things that can be attributed that give the soil its strength, its shear strength. First of all, we talked about that soil will resist in shear. When it's resisting in shear, think about this portion is going down, this portion is going up. At a microscopic level, not microscopic, the minute level, you will actually see that the particles are granular, isn't it? This is not a solid material. Particles are granular. And now I have a stress force going like this. So the more interlocking these particles have, denser their gradation is, more their shear strength will be. If I have a looser gradation like this, you see the particles have some space where they can actually move under this load. So they will form a tighter um, configuration. But here, when they're already at a very tight configuration, it is difficult for them to, because right here they have to climb up. So that is the first thing, is the interlocking of particles, but that is mostly for coarse grained soils, not for fine grained soils. Frictional resistance to sliding between solid particles. This basically is second thing is frictional resistance. Frictional resistance is same as what we used to study in our 11th standard. You have a block on a slope. As you increase the slope, the force, the load above normal stress uh, is because of the weight, and then you will have a W sine theta, W cos theta. So based on this angle of friction, we used to say that what will be the, based on the weight and this angle, we used to say that what will be the static friction or dynamic friction, something that we used to talk about. It's almost same for soils. You take two soil particles, and this is their normal force and tangential force. Then you take tau is equivalent to n tan phi, where phi is the friction angle, n is this normal stress, and tau is your shear strength. So initially, this was the equation that used to be followed. Tau is n tan phi, but this actually means that if there is no normal stress, then there is no shear strength. But this was true for some of the soils, like coarse grained soils. But people could see that this is not true for some other soils, like fine grained clays, that exhibit some shear strength even if they have a very low or no angle of friction or n. So uh, that was then considered to be because of cohesion, because of the actual what we could say cohesion you will find in clays. You will not find cohesion in silts. So in clays, it is by virtue of the uh, properties of the particles, that they are electrically charged, they have an electronegative character, and then they attract, and they are bonded by water, and the kind of crystals they have, the clay structure, and all of those things. Because of that, you can see that if you want to uh, dig a pit in sand, you will not be able to do without first providing the support and then digging it out, because this will keep on this slope will keep on failing. But let us say a relatively wet clay, let us say, you can provide to a certain height vertical cut in a soil, in a clay, that we can say is because of um, the cohesion it possesses. So after that, we would write tau is equivalent to C plus n tan phi. And in a tau sigma diagram, we could plot this as a straight line. Y is equivalent to mx plus c. Yes, Arav?
What is n, madam?
N, M.
N. C plus n tan phi. It should be
This is
sigma.
normal. Yeah, normal stress.
Yes, yes. Okay,
Okay.
fine.
So tau is C plus sigma tan phi. This is basically y is equivalent to c plus m times x. This is your intercept, and this is your m is basically tan phi. So this will be phi, and this is x, this is y. So this is the shear strength envelope that this line represents. It means that given a particular normal stress, what will be the maximum shear stress that the soil will be able to bear? Beyond this, the soil will fail. So, okay, shear strength, a pretty many of the concepts used in some of the basic mechanical force can be employed to explain various phenomena in soil. That is true. And then at the point of impending motion, so here we are talking about friction in its basic form, tan phi mu, and how it relates to soil. So this is all these mohors, like how they used to. This is all computational, not much logic. Obviously logical, but like more about computations, less about concepts. So this is the Mohr circle. If anybody wants more detailed discussion on these topics, please let me know. Share strength, share strength. Okay, so let's first talk about principal stresses and normal stresses. Did I mention, like, have I talked about principal stresses in the class?
Yes, yes, ma'am. Yes, ma'am.
Huh? Have I explained the concepts of principal stresses?
Professor explained that.
Yes, I mean, in our interactive sessions, have I discussed them?
Mm. No, madam.
Okay, okay. So let me start by, I will briefly tell you about a generalized concept. These, let us say that this is a body, and I want the stress state at inside the body. So what I will do is I will just slice this body, reveal this point that I, okay. Now this point will have stress because, see, I have sliced this, but I'm not actually broken the body. So the what will initially this had some stresses like this, stresses like this, stresses like this, internal stresses, isn't it? So it will still have these internal stresses, say like this, and I have replaced all of these stresses on the opposite side with one resultant, let us say T. It can be in any direction. So on this plane, in general, this point was experiencing a stress in this direction. It had stresses in many directions, but the, let us say it's like a tug of war. Both of the parties, or if it were more than two parties, both of the parties are pulling. There are stresses in both directions, but there is a general direction in which we can say that the motion is going or the stresses are more. So this is being tugged like this, let us say. It can also be in the opposite direction, but then after calculations, if the value is negative, then it is the opposite direction, so that is not an issue. Now I want to define the stress on this point, stress on a point. You know that there are uh, infinite ways that I can define the direction in which the coordinate axes, for example, lie. Let us say I've taken one direction and I have split this r, rx, ry on this plane that I had arbitrarily chosen. And because your stresses are basically second order tensors, you will have an Rx that basically you will have an Rxx, Rxy, and then you will have an Ryx, Ryy. So it will be something like this, something like this, something like this. Then you will have something like this, something like this, something like this, something like this. This will be Rx, this will be R1, let me say, this will be R2, then this will be R1X, 1Y. This is called basically a Cauchy tensor. In three dimensions, you have sigma x. In two dimensions, you have sigma xx, sigma xy, sigma xz. Three dimensions are after all. Sigma yy, sigma yz, sigma zz, and sigma. Then this is symmetrical. Okay. So these are the stresses that you need to know to define the actual stress on a point. When you know all of these stresses, then you can actually completely say that I know the what is stress at this point. But as you can see that this is quite a tedious task. Why? Because these stresses depend on the orientation of this plane. If I had taken this kind of a plane, I would have ended up with some different stresses. If I now rotate this plane like this, because this is arbitrary, I would have had another different Cauchy stress tensor. So it does not mean that the actual stress is changing at this point. It means that because the stress is basically telling me, this value is telling me how much uh, uh, magnitude of x is acting in the x direction. This is telling me how much magnitude of x is acting in the y direction. This is telling me how much magnitude of y is acting in the z direction. So it is dependent on the directions. As soon as I change the direction of my plane, these values will change. But when I impose it on this point, I will always get scalar. When I calculate the scalar or the vector, I will get the same values. So in order to first of all reduce the number of unknowns here, and secondly generalize this, what we know is that at every point, if we rotate this plane in such a way, there is a chance that we will end up in a Cauchy stress tensor that looks like this. Okay, this kind of a tensor, see x, y, z are fixed, x, y, z are fixed. So what was not fixed was the resultants of the first like basically I had this origin system, and this point had second order tensor stress, resultant stress. So in x, in the x direction, it resulted in a vector like this. In the y direction, it resulted in a vector like this. Okay. And then I have to decompose it based on the first we decompose it based on the this orientation of this plane. Then we decompose it based on the orientation of the axes. So that is why we need to decompose them two times. So here what happens is that now it no longer depends on the direction of the axis, because no matter what, these three will remain same for your Cauchy tensor when you are um, not in this state, or when you are in this state, these will always remain same. Only thing changes is the these elements. So we find the direction in which we get this kind of a Cauchy tensor, and in that direction is called the principal direction, and these stresses are called the principal stresses because they do not depend on the direction of the plane that you have taken, and they generalize the whole thing, and they make everything comparable. That is the concept of principal stresses. And then when you talk about Mohr diagram, you can either calculate the values in terms of principal stresses or total stress or Cauchy stresses. But basically, the concept is for principal stresses, and from the concept, what we have done is we have back calculated the idea that what if we did not have principal stress, what if we had normal stresses, then what would have come. Okay. So I think we can start some questions. Point loads of magnitude 100, 200, and 400 at B, C, and D respectively, act at B, C, and D respectively, determine increase in vertical stress at a depth of 6 meter below A. Okay, so this is like a top view. Change the color. Okay, this is like a top view, and what they are saying is that there is a load here, there is a load here, there is a load here, which is 100 kilonewton, 200 kilonewton, and 400 kilonewton. And we want to determine, let us say, if this was A, then the at a distance we would have had B. But if I just look it from the side view, I will have B on the same uh, at the same place but differing in L. Then we have D, C. We want to calculate increase in vertical stress at a depth of 6 meter below the point A. Okay, so we need to calculate the stress here. So if you see, because of B, you will have, let's actually draw a parallelogram. So B Z is 6 meter. This our distance will be, we will calculate it. This is 6 meter. And then D distance will be based. First of all, we have to calculate this. And then we have C will be acting like this. Is it not? So these will be the directions of the how these loads are. This is 6 meter. CD is 3 meter. So it's basically something like here. So this is 6 meter, this is 3 meter. This distance B. This will be 6 square plus 3 square. And between A and C on the top view, we will have 6 root. And then we will know this. We will know this. Then we will have a triangle with 6. C was AC was 6 root 2. 6 root 2. Then we have C A, A, A dash. Then we have a triangle with 6, 6 square plus 3 square. This will be D, this will be A, this will be A dash. Then we have a triangle A, A dash, and B. This will be 6, this will be 6, this will be 2 root 6, 6 root 2, sorry. So we will have 100 here. This is clear how we got these values. Is this clear?
Yes, madam.
Okay, we can start an Excel sheet. We can put in these values. Top view, we have A, points we have B, C, and D, and their distance with A and A dash. AB is 6 meter, AC, let's come back to it. Then AD, AC is 6 root 2. AD is square root of 6 square plus 3 square. 6 square is 6, 6, 36, 3, 3, 9, 6, 3, 40. Acha, why am I not doing it here? 6 into 6 plus 3 into 3, 45. Square root of 45. AD. And then A dash C was, let us take H as 6. That is A dash. This will be square root of AB square plus AA square. AB dash, then we will have AC dash, and then AD dash. Okay, so basically Z, and these are the values of R, RB, RC, RD. So Z. We have R, and then we have X, Y. We have a Z, 6, 6, 6. So what is our equation? Using this equation, that is, write it here, delta sigma Z equals Q Z Q by X plus X Z. Basically R square. R we calculate from here. This is R. This was just the distance. We call it L. R square. We can have Q Z. This would be into Z. Z divided by pi. Let's write it square plus Z square. Can you please check the formula? I think there is a square here. I need to check the formula. In rectangular coordinates. This, this is x, y. We calculated this, then we calculated this, capital R. This 3q by 2 pi z square. अच्छा, 3q 3 into q into divided by 2, 3.14 into z square. Let's call this term 1. Then term 2 will be 1 1 plus r square by z square raised to power 1 plus r square by z
R
square.
square, you need to use the bracket, madam.
Hmm?
For R square, you need to use the bracket.
No, actually it's same because it is in
Otherwise,
multiplication. It will be same. Then we will have sigma z
three by
T1
three, three.
over T2. Okay, we did not add A. A also has a load, isn't it? Or am I wrong? Did A have a
I
load?
saw it at the beginning only. You are not given.
Hmm?
I saw at the beginning only. You are not given any load.
No, no load.
Even we can do it, madam, without load at point A. Also, we can do.
Yeah, yeah, we can do it. We are doing it. I thought that there was another load. Then we would have to have used another formula. Then R would
If
have
there is
been zero, na?
a load, you can give us. We will make a homework for that.
Okay. Uh, just a moment. Okay. Okay. You cross check this question. I'm having some doubts in this question. You cross check and let me know in mail what you find the answer. Okay. So next question. Can we take a 5 minute break, please?
Yes, madam. You can enlarge the question, madam. We'll solve it in between.
Mm, okay, you can uh,
Yeah.
solve this question.
Little.
Okay, let's see. Determine the vertical stress increase delta sigma at a point A with the following values: Q1, Q2, X1, X2, Z. Okay, so we will have again delta sigma Z equals Q Z cube pi X square plus Z square. There is no R because these are in same line. Square. Then for load 1, we have Q 90 kilonewton per meter. Then we have X, this is 4, this is 2, this is 6.5, then Z is 3 meter. Z is 3 meter. So if we add, let's calculate this.
0.588.
Mm-hmm.
Plus
Plus,
24.02.
okay, do this calculation 325 into 3. out of
24.61.
24.6, yeah.
Chart box I mentioned, madam.
Yes, yes, I saw. Thank you very much. Thank you.
Come on.
And yes, okay. So we have some more questions. Okay, we can start these questions. I'll do one more question, and I think I'm not feeling very well today. If it's okay, and the next two questions I would like you people to try. If you have any, you can let me know. Okay. So the magnitude of stresses on the soil element are sigma x is this much, sigma y is this much, then tau. See, because there is tau, that means that these are not the principal stresses. So your Cauchy stress tensor will be 120, 300, and because we have taken it in a plane strain condition, we will take 2 cross 2 only here. Then we have 40 and 40. This will be our Cauchy stress tensor. Then theta equals 20 degree. Magnitude of principal stresses. So one thing that we can do is uh, we usually solve it like an eigenvalue problem. So the I don't know if rest of them are 0, 0, 0, but let's say for example they are. Then we will have I1 minus 120 plus 300. I2 equals 300 into 120 minus I3. Actually, I will not be able to solve it like this. Just a minute. Okay. Let us say that sigma is the mean of principal stresses. Then x sigma times lambda equals 0. This is the eigenvalue problem that I was talking about. But because this is not in 3D, I'm not sure if that will work. So we will go with our normal way in which we calculate insults. Sigma y by 2 plus sigma y minus sigma x by 2 cos 2 theta plus tau xy sin theta. And then we have tau n as sigma y minus sigma x sin theta minus tau xy cos 2 theta. Principal stresses are given as sigma x plus sigma y plus minus square root of sigma y sigma x over 2 square plus tau xy. So plus will be for sigma 1, minus will be for sigma 3. So we will have sigma x is 120 plus 300 over 2 plus square root of 300 minus 120 over 2 square plus 40 square. Let's calculate this. This comes out to be something
308.
0.5.
0.5 and 111.5
Okay.
kilonewton per meter square, madam.
Sigma 3, sigma 1. Normal, can you calculate normal and shear stresses on the plane maybe?
Three 74, madam. Normal stress.
Shear stress?
374, madam. Normal stress. Shear stress is 28 kilopascals.
Just a moment. Uh, okay. Please check the sign convention here. I think the sign convention requires the tau to be negative. Please check that and let me know. Okay, I think that is it for today. There is one more question that you can try out on your own. Yes. Okay, thank you very much.
Thank you, ma'am.